So let's imagine we had a chunk of silver metal and a chunk of copper metal. And let's say we connected these two metals with some conductive wire. What's going to happen? Well, something important to realize is every metal has its own intrinsic positiveness. Where silver has a very high intrinsic positiveness, where copper has a very low intrinsic positiveness. And this positiveness we refer to as a reduction potential. And you can look into any old chemistry textbook and see that the reduction potential of silver, aka the positiveness of silver, is positive 0.8 joules per coulomb. However, the reduction potential of copper, aka the positiveness of copper, is 0.34. So therefore, because silver has a more intrinsic positiveness, a more positive reduction potential, electrons are going to want to flow towards this silver. And that makes sense. It makes sense that these negatively charged electrons are going to be attracted to this intrinsic positive silver. And this is essentially how battery works. You have two materials with different intrinsic positivenesses, aka different intrinsic reduction potentials, and the compound with a more positive reduction potential will have electrons flowing towards it. And we know whenever any molecule gains electrons, it gets reduced. So we call the side of the battery that gets reduced, that gains the electrons, a cathode. And that's the way you define a cathode. A cathode is the side that gets reduced. And the side that loses its electrons gets oxidized. So by definition, the side that gets oxidized is an anode. So this is something you just need to memorize. The side that gets reduced by definition is the cathode, and the side that gets oxidized by definition is the anode. And I know it's a little difficult to memorize, so a trick that's taught to us is an-ox, red cat. Anode gets oxidized, reduced is the cathode. So if you just simply memorize a red cat, you'll remember it's the cathode that gets reduced, so therefore the anode has to get oxidized. So that's just a simple way to memorize this. So let's try another example. Let's say we have a chunk of gold metal and we have a chunk of chromium metal. What's going to happen if we connect these two metals with a conductive wire? Well, we would look in a chemistry textbook and see gold has a reduction potential, aka an intrinsic positiveness of positive 1.5. And we would see chromium has a reduction potential, aka an intrinsic positiveness of negative 0.74. So therefore, comparing the two reduction potentials, we see gold has a more positive reduction potential, aka gold has a more intrinsic positiveness. In fact, chromium is in the negative range. So therefore, we connect these two metals with the wire. It makes sense that negatively charged electrons are going to be attracted to gold because gold has a more intrinsic positiveness. So it's going to attract these negatively charged electrons. So therefore, the compound with the more positive reduction potential is going to gain electrons and it's going to get reduced. However, another way to determine which side the electrons will flow is to compare the oxidation potentials of both compounds. So the rule of thumb is whenever a compound has a reduction potential, its oxidation potential will be the same magnitude but opposite sign. So again, we see gold has a reduction potential of positive 1.5. So therefore, gold's oxidation potential will be negative 1.5. Same magnitude, opposite sign. And chromium has a reduction potential of negative 0.74. So therefore, it would have an oxidation potential of positive 0.74. And the rule of thumb is the compound with the more positive oxidation potential is going to get oxidized. So we see chromium has a more positive oxidation potential, so therefore it's going to get oxidized and lose electrons, which confirms what we already learned. So you can either focus on reduction potentials or oxidation potentials. And really, textbooks usually focus on reduction potentials, but you can easily find the oxidation potential by just flipping the sign. However, another way to determine which side the electrons will flow is to determine the E cell of a theoretical battery. And what's important to realize is whenever a battery has a positive E cell, that battery will allow electrons to flow. Exactly how, if a chemical reaction has a negative delta G, that chemical reaction will be spontaneous. It's the exact same idea. If a theoretical battery has a positive E cell, that battery will occur spontaneously and electrons will flow spontaneously. So how do you determine the E cell of a battery? Well, first you have to imagine a theoretical battery. For example, let's theoretically imagine electrons flowing from gold to chromium. So how do you determine the E cell of this theoretical battery? Well, you need to see the side that gets reduced that gains electrons. You need to find the side that gets reduced and determine its reduction potential. And then you need to find the side that gets oxidized and determine its oxidation potential. And then you need to add those two values. So again, in this theoretical battery, chromium gets reduced. So therefore, you would need to find chromium's reduction potential, which we know is negative 0.74. And we see gold is getting oxidized, so we would need to find gold's oxidation potential, which we see is negative 1.5. So once you determine the reduction potential of the compound that's getting reduced and the oxidation potential of the compound that's getting oxidized, you simply add them. So if you add these two values, you would get an E cell of negative 2.24. And remember, only when a battery has a positive E cell will electrons flow spontaneously. But we see this theoretical battery has a negative E cell, so therefore electrons will not flow spontaneously. So therefore this theoretical battery will not work. However, let's imagine another theoretical battery. Let's imagine electrons flowing from chromium to gold in this opposite direction. Does this theoretical battery have a positive E cell? Well, again, you find the side that's getting reduced and you find its reduction potential, and then you see the side that's getting oxidized and you determine its oxidation potential. So in this theoretical battery, gold is getting reduced, so we need to find gold's reduction potential. And we see chromium is getting oxidized, so we need to find chromium's oxidation potential, and we need to add those two values, and that will give you the E cell. And in this theoretical battery, it has a positive E cell. So therefore, electrons will spontaneously flow in this theoretical battery, going from chromium to gold. So this is a feasible theoretical battery. So therefore, we know electrons will flow from chromium to gold, which is again what we already determined earlier. So the point is there are three ways to determine which side the electrons will flow. One, you can compare both of the metals' reduction potentials. And remember, the compound with the more positive reduction potential has a more intrinsic positiveness, so therefore it's going to attract these negatively charged electrons. So we see gold has a more positive reduction potential compared to chromium, so therefore gold is going to gain those negatively charged electrons and it's going to get reduced. The compound with the more positive reduction potential will get reduced. However, we can also compare both metals' oxidation potentials. And remember, the rule of thumb is the metal with the more positive oxidation potential gets oxidized. So we see chromium has more positive oxidation potential, so therefore it's going to get oxidized and it's going to lose electrons. And also we can find the E cell of the battery. And again, to determine the theoretical E cell, you imagine the side that gets reduced and find its reduction potential. Then you imagine the side that gets oxidized and find its oxidation potential, add those. And if you get a positive E cell, you know that theoretical battery is feasible and the electrons will flow in that direction. But personally, I like to focus on reduction potentials. I think it's most simple. So again, if you have an exam and you have this particular question, all you need to do is compare both of the reduction potentials. And the metal with the more positive reduction potential has a more intrinsic positiveness, so it's going to attract negatively charged electrons, so it's going to get reduced. So again, we already determined if you connect a piece of chromium metal with the piece of gold metal and connect them with a conductive wire, we already determined that the electrons are going to flow towards the piece of gold. And we determined the E cell of this battery, and it had a positive E cell, so this is a feasible battery and the electrons will flow towards gold. However, in reality, it's a little more complex, and if you connect a piece of chromium and a piece of gold, electrons will not flow. So in reality, in order to allow electrons to flow, you would need this kind of setup. For example, you would need a chunk of gold metal in a solution with these ionized form of these gold ions. And you would need a chunk of chromium metal in a solution with these ionized form of these chromium atoms. And just an important rule of thumb is whenever an atom is in its neutral form, it's going to be in a solid chunk of metal. However, whenever an atom is in a charged or ionized form, it's going to be dissolved in a polar solvent. For example, this chunk of metal is made up of neutral gold atoms. So whenever we have a chunk of metal, it's made up of neutral gold atoms. However, in this solution, we have these ionized forms of gold. We have these gold ions dissolved in this polar water solvent. And that makes sense because we know like dissolves like. So it makes sense that these charged ionized form of these gold atoms are going to interact with this polar water molecule. So it makes sense that these ionized form of gold is going to dissolve in this polar solvent water. And the same thing with chromium. So we would really need this setup to allow electrons to flow. So why do we need this particular setup to allow the electrons to flow? Well, remember, we find gold's reduction potential. So we look in a chemistry textbook and we see gold's reduction potential. And in reference to gold's reduction potential, we see this particular chemical reaction. Why do we see this particular chemical reaction? Well, in reality, what's going on is these ions react with electrons to form solid gold. So in reality, that's what's going on. It's these ions of gold that react with electrons to form solid gold. So essentially, these electrons are going to flow. These electrons are going to hover around this chunk of gold metal. And then those electrons are going to react with these ionized form of gold. And what happens is these ionized form of gold reacts with these incoming electrons to form solid gold. And again, we see that in this equation. We see the ionized form of gold reacts with electrons to form solid gold. So therefore, these ionized form of gold is going to react with these incoming electrons to form solid gold, this neutral gold. And again, that makes sense. We have these ionized form of gold. They're going to react with these negatively charged electrons. So when we have these positively charged ionized form of gold react with these negatively charged electrons, they're going to form neutral solid gold, this neutral solid gold. So it makes sense as time goes on, as these electrons flow, these electrons are going to react with all these ionized form of gold, and these ionized form of gold is going to gain those incoming electrons, and these ionized form of gold is going to form solid gold. So as time goes on, we're going to see a chunk of gold building up, and this chunk of gold is going to get larger, and we're going to have this chunk of gold metal. And we see that. We see as time goes on, these ionized form solid gold, and that's why we see this chunk of solid gold. But what's going on this side where the chromium is getting oxidized? Well, again, if you look in a chemistry textbook, you would see the oxidation potential of chromium. And in reference to the oxidation potential of chromium, you would see this particular chemical reaction, where neutral solid chromium essentially forms electrons and this positively charged ionized form of chromium. So we have solid chromium forming ionized chromium and electrons. So in reality, that's what's going on in this side. Essentially, electrons are flowing away from these solid chromium atoms. And as these solid chromium atoms lose electrons, they form more ionized form of chromium. So again, essentially imagine these neutral chromium atoms. These neutral chromium atoms lose these negatively charged electrons. As these neutral chromium atoms lose these negatively charged electrons, they form these positively charged chromium ions. And that makes sense. Solid chromium loses negatively charged electrons, so what's left is a positively charged chromium ion. So as time goes on, these neutral chromium atoms are going to lose negatively charged electrons, and the moment they lose those negatively charged electrons, they form these positively charged chromium ions. And again, as time goes on, we're going to lose more chromium solid, and we're going to form more chromium ions. And we see that in the half reaction. So it makes sense. As time goes on and as these electrons flow, this chromium solid is going to get dissolved because all these neutral chromium atoms lose their electrons and form more chromium ionized form of these atoms. So as time goes on, we're going to lose, this metal essentially is going to dissolve. It's going to dissolve and lose what was once neutrally charged chromium atoms because they lost electrons and now they formed these ionized form of chromium atoms. So the reason why we need this particular setup to allow electrons to flow is because essentially what's going on is, imagine these neutral chromium atoms. These neutral chromium atoms lose these negatively charged electrons. As they lose these negatively charged electrons, they form these positively charged chromium ions. And then these electrons flow, and what happens is these charged form of these gold ions essentially react with these incoming electrons to form neutral gold. And again, we can see that going on in these half reactions. That's what these half reactions are showing. But what's going to happen as this reaction continues? Well, as this reaction continues, again, these neutral chromium atoms lose negatively charged electrons, forming these ionized form of chromium atoms. So therefore, this concentration of these positively charged chromium atoms is going to increase. So this side's going to get more positively charged. And as these negatively charged electrons flow, we know these positively charged gold ions react and gain those negatively charged electrons, forming neutral gold. So if these electrons continue to flow, neutralizing these positive charges, we see this side's going to get more negatively charged. And that makes sense because negatively charged electrons are flowing. So as this reaction continues, this side's going to get more positively charged because it's going to gain more positively charged chromium ions. And this side's going to get more negatively charged because it's going to gain these negatively charged electrons reacting with these positively charged gold ions to form neutral gold. So as this reaction continues, this side gets more positively charged and this side gets more negatively charged. And if that continues, eventually this reaction will cease to work because as the side gets more positively charged, it's going to eventually draw in those negatively charged electrons. As this side gets more positively charged and this side gets more negatively charged, those negatively charged electrons are going to start to flow in this direction. So therefore, in order to allow these negatively charged electrons to continue to flow in this particular direction, we need to neutralize these charges. Because again, as this side gets more positively charged, eventually, as it gets more and more positive, it's going to start drawing those negatively charged electrons. However, if we add a salt bridge, this salt bridge can neutralize these charges. Because this salt bridge has a negatively charged anion and a positively charged cation. For example, chloride ions and potassium ions. So essentially what happens is as these negatively charged electrons flow, and as this side gets more positively charged, these negatively charged chloride ions are going to dissolve. They're going to essentially dissolve, and these negatively charged chloride ions is going to neutralize this positive charge. And as these negatively charged electrons flow and this side gets more negatively charged, these positively charged potassium ions are going to flow and neutralize this negative charge. So essentially this salt bridge essentially neutralizes these charges. And as this salt bridge neutralizes these charges, it's going to allow these negatively charged electrons to continue to flow. And in reality, the salt bridge is closing the circuit. But the point is, in order to allow a functioning battery to work and to exist, you need a salt bridge to neutralize these charges. But essentially, this is what we call a galvanic cell or a voltaic cell, or really you can just think of it as a battery. But the point is, if you're given one of these questions on the MCAT or in a chemistry exam, all you need to do is compare both of the metals. And what you need to do is find the reduction potential of both of the metals. And the metal with the more positive reduction potential, you know has a more intrinsic positiveness. So the metal with the more positive reduction potential has a more intrinsic positiveness. So you know the electrons are going to flow in that particular direction. And because gold has a more intrinsic positiveness and a more positive reduction potential, we know gold is going to gain the electron, so therefore we know gold is going to get reduced.